So, chapter 17. Chapter 17. Interference, diffraction, and standing waves. 3 different areas. There's a lot in this topic. Let's start with diffraction. Okay. So to start with diffraction, we go up to page 2 over here. Waves and wave properties. Huygens principle. Okay. So to understand diffraction, which kind of underpins everything that happens in this area when a wave is, different ways that you can manipulate a wave, is if you look at a wave front, for example, this represents a wave front. And a wave front just moving like a wave parallel to a beach, just moving in, okay? So a straight wave like that will move through a medium, okay? And if it hits an opening, all right? If it hits an opening, what will happen is it will diffract through that opening. So a diagram of that is this here. So this is what diffraction looks like. So if a wave hits an object in its path, all right, it will tend to bend around it, okay? So you'll end up with little turns in the edge of the waves. Okay, and that's the idea of diffraction, where the wave will bend around an object or an opening. Down here, the version that we look at the most is when a wave hits an opening. Okay, when a wave hits an opening, you end up with the wave front bending through that opening. Okay, now you'll notice that there is a difference on whether or not the opening width is comparable to the wavelength. So when you look at these lines, you're looking at peak to peak. So in the middle of them, there's a trough. So you're looking at the peaks, all right, as it's coming through. So if you measure the wavelength peak to peak and say to yourself, well, that's within the same order of magnitude as the opening, then you end up with something like full diffraction, okay? All right. If, on the other hand, your wavelengths are really, really short, but the opening is really, really wide. I mean, if you think about it, it makes sense. It makes sense that you're going to get most of your wavefront just coming through, okay? Most of the wavefront comes through, and it's just going to bend a little on the edges, and you get a little bit of diffraction. Now, the model that we really use to explain what the difference is let's say you're lining up outside Festival Hall, and you're waiting for your band to come on, and you're waiting to get in, okay? But they're tuning up or like doing sound check inside. What you tend to hear through the doors, if the doors are open and you're around the side of the door, okay, what you tend to hear really clearly are the drums, you hear the bass guitars, things like that, okay? Why? Because the wavelengths of those instruments are actually somewhere in the right order of magnitude of the door opening. So as they go through, they arc across and you end up standing over here. So you can stand over here and you can see that the sound of the bass and the drums is bending around where you can hear it. These sort of guitars, high-pitched instruments, they tend to go straight through, and you sort of end up with a bit of a shadow for those sounds. Okay, so the deeper sounds seem to sound better when you're around an obstacle because they're bending around, okay? So that's the idea of diffraction. So a wavefront hits an opening and will bend, and the amount that it bends depends on what the ratio of the opening to the wavelengths is, okay? When the wavelength is greater than or equal to W, W being the opening, you get basically full diffraction. There is a nice little, I've never seen, other than in this unit, this use of the less than symbol. So when the order of magnitude is greater than or equal to 1, okay, so the ratio of the wavelength to the opening, you get full diffraction, 180 degrees. It bends all the way around wall to wall, okay? Lovely. Then they've got this version here. If the ratio is much less, that's what that means. How weird is that? Much less. Because it's like 2 little less than symbols. I've never seen it used like that anywhere other than here. Much less than 1, then there is very little diffraction. In other words, if the wavelength is really really, really small and the opening is really, really wide, you get very, very little diffraction. So if you think about it for a second, it does kind of make sense if you're trying to picture it. All right? So that's diffraction. So you will see I've created a help sheet, obviously. This one has pretty much everything right from the start, from wave basics all the way up, okay, to light basics and standing waves. Everything is in this particular help sheet, and it's nice in color as well. You can borrow bits from that if you want to, okay? Everything in there that we're going to be studying today is in here, all right? So right down here in this corner, you've got the diffraction, a little picture. That's how I encourage you to do this in your own help sheets. You put a little picture in, and that way it reminds you of what it's supposed to be if you're on the run, you know, in the hurry, trying to answer a question. So it's like, oh yeah, that's what that's about. Okay, so it's always good to have little keys. Interference patterns, page 3. All right, so what happens is we've got, we also have interference, okay? So let's say that the clearest, the nicest version of interference is, let's say you have, this diagram doesn't show it very well, but this diagram is really, it's like, remember we mentioned double slit interference the other day? And what we're talking about here with double slit interference is there's a wall, we have a source of waves on one side of the wall, and those waves are approaching the wall, you know, in a nice regular pattern. They hit the wall, and the wall has a couple of gaps in it. Those gaps act like point sources, and the reason you do it like this is because those point sources are now in phase. They are sending out a wavefront at exactly the same time because they're bits of the same wavefront. That's why. So that way you can time them, right? So the waves come out, and this is what you're seeing here. This little wavefront bends 180 degrees, and this one 180 degrees, and they keep moving, and as they move out, they interact with each other, okay? And as they interact with each other, funky things happen, all right? So funky things happen is there's lots of waves. The waves are meeting each other. This bit of the wave is meeting that bit of the wave. And remember what we were talking about the other day? Superposition. In superposition, the Y values add up, and the waves, if you've got two waves on a crest, they'll add up and the wave will be a little higher. But if you've got a wave on the top and a wave on the bottom, they can cancel each other out. Well, that's what we look for. What we look for are regions where crests meet crests, troughs meet troughs, which just means those crests are bigger and the troughs are deeper. But where the really fun part is when crests meet troughs and they cancel out. As the energy passes, they cancel out and you end up with like a dead spot, like a node. All right? And so these lines here represent nodes. Okay, well, nodes and antinodes it looks like because you've got a different color pattern there. All right, there is a cool demonstration of that, which I think we're already up to. Yeah. So I've got my Ozito laser pointer thing, it's laser level, which I actually used on the weekend, and a diffraction pattern. Now on here, you see little gaps of light, okay? But what those gaps are, they're actually double slits. But obviously the slits have to be really, really, really thin because it's in the order of magnitude of light waves. And so the light waves, obviously those slits are tiny, okay? To do anything, to get the lambda over W ratio to the point where the light will actually bend through the slits, okay? So we take this, and so those little gaps are actually double slits, all right? So we take the laser, and we shine it on the board, and we try and get a steady hand and hit one of them. Let's try that one. Oh yeah, that's nicer. See that? Now can you see the all the little gaps there? Notice the center of the dot is very, very bright. And as you move away from the centers, you see dark bands. You see dark bands, and they get dark and light bands as it moves across from edge to edge, right? Please tell me you can see that, right? Yeah. You don't see the bands? All right, so when you look at the very, very first crest that comes through, right? The first maximum that comes through, okay? Now, the light is in the medium. The light travels at the same speed in the medium. So if they both start off in the same moment, they should arrive at the same moment. But if you look through the middle, right through the middle in the line in between these guys, right here, that distance there, that separates them, okay? The distance from here to here, which is the very middle, okay, has to be the same as the distance from here to here. Okay, so those two distances are exactly the same. What we say then is that the path difference between those two is 0. Okay, so they travel the same amount of distance, which means if a crest comes out with a crest, they meet at the board. They meet at the board as a maximum, right? Which means that the middle is always a bright. It's always a bright band. Okay? Because the path difference in the middle is always 0. It wouldn't matter if you took the screen and shifted it out here or brought it in. The path difference to the middle is always the middle. It's always the same. Okay? So the distance between here and here has to always be the same. It's a nice, beautiful, symmetrical pattern. All right? Okay. Now, where it gets a little bit more interesting is, let's say we go over to the next bright band, right here. Now, what you're really looking at is the first wavefront arriving at the same time as what? The second wavefront from this one, because you're going on an angle. So the distance between here and here is shorter than the distance between here and here. But if it is shorter by the correct amount, then you can time it so that the two crests, even though it's the first crest from this one and the second crest from that one, they meet at the screen. They meet at the screen at the same time and interfere constructively. Another bright band. So you know that for the first bright band across, now we call this n equals 0, okay? Then you go n equals 1, okay? And then over here will be n equals 3, okay? And yes, it's symmetrical, okay? Yeah. That has to be one wavelength longer. This line has to be exactly 1 lambda longer than this line, and you will get a bright band. Okay? Over here, if you went to the next bright band, which is over here, then that will be exactly 2. It'll be exactly 2 lambda longer. So the difference between the path from here to here and from here to here will be 2 lambdas. Here, it'll be 1 lambda from here to here. Here, it is 0. From here to get to the middle, it is 0 lambda. So when we're talking about path difference, what you're talking about is the difference that the waves actually travel to get from the source to the screen. That's the path difference. I impress that carefully because then as soon as you mention another thing that we do next, things start to get muddled up and people start to mix them up and then you get confused, all right? But the path difference is quite literally the linear sort of, the walking straight up to that spot, okay? if those distances are exactly a whole number of lambdas apart, then you know that you have a path difference that will lead to a bright spot on the screen, okay? So the path difference, now you'll see it written like this, and you'll also see it written like this. Now, they may go, this is S1, S2, and we'll call this point P, all right? So another way that you'll see this expression written is the distance S, path difference will be what? It's the long one, is S2 to P, take away S1 to P. See that one there? Okay? Should be, for a bright band, a whole number of lambdas. Okay? So if you want to know what's the path difference between S1 and S2 and the middle band. Okay? So to the middle band, the path difference is, well, the middle band is n equals 0. All right? 0 times lambda, 0. That's the difference between them. There is no difference. They're the same length. Get it? Makes sense, right? If I want to go over to N1, what's the path difference there? Well, I know S2P, take away S1P, should be 1N. Or 1 lambda. Should be 1 lambda. There should be 1 lambda in length difference. Then I know that a crest reaches a crest or a trough reaches a trough, and they construct and they are bright. They're always bright. Just like the laser that I showed you. All right? They're all the bright bands. They're all exactly 1 lambda apart in difference. Okay? Don't want to labor the point too long. All right. Okay. Now I know what you're thinking. What about the dark bands? I'm like, that's a really good question. So this is the condition. These are the conditions for bright bands. Path difference, bright bands. Okay. What about dark bands, I hear you call? For dark bands, all right. For dark bands, the condition is you want a trough to meet a crest, and they cancel each other out for that instant, all right? So for a trough to meet a crest, how far off do they need to be? Yeah, a half lambda. They have to be offset by exactly a half. And if they're off by a half, then you get a trough slamming into a trough slamming into a crest, and bam, it flattens out. There's your dark band. So they have to be off by half. So this is now the same, except for, instead of for bright bands, for dark bands, it's not n lambda, it's n take away a half lambda. So you need to go from the middle. Oops, I've moved all these, haven't I? Okay, from the middle. Let's get rid of all of this here so we can look at this one properly. So if n equals, I could just move the screen slightly. Yeah, it's a bit better. For the first dark band, I have to say, well, I can't go all the way to lambda. I have to go to lambda, but I've got to come back a half lambda. Okay, so I go 1 take away a half, it's a half lambda. So what's the path difference for the first dark band or the first node? It's whatever the lambda is, the wavelength is, divided by 2. Okay, so this gives me the conditions for dark bands. And that's what the questions are. The question will ask you, oh, is it a dark band or a bright band? Many questions will be pitched as there's 2 speakers that are in phase and I'm walking on the line exactly between them. Will I experience loud and quiet spots? Well, no, actually you won't, because I'm walking in the line exactly between those 2 speakers. So I'm always the same path difference from both speakers. The middle is always loud, okay? But what if... Pardon?
Anywhere else experience?
Well, anywhere else, what if I was walking on a line sideways for two speakers that are in phase? Well then, yes, because what you're essentially doing is you're walking through light and dark bands, and you wouldn't hear nothing, but you would hear loud, and then you would get kind of quiet, and then you get loud again, and you get kind of quiet. So there's lots of things in sound that you can play with where you play with that whole constructive, destructive interference. And sound does the same thing. All the maths is exactly the same, except that in this, the light wavelengths will be tiny, whereas sound waves, you'll be like, okay, the path difference is 1 meter. So where do I see, like, will there be a loud spot or a quiet spot? It's exactly the same. The next thing that we have are fringe spacings. Now, that's the other thing that they can ask you during questions and in SACs and the exam. Fringe spacing. So the fringe spacing is just this. What is the distance between the first bright band and the second bright band? There's your fringe spacing. Delta X, they call it. Okay? So it's really simple to... Now, obviously... Sorry, I say obviously. Maybe it's not obvious, okay? I'm old and I've done this a billion times, so yeah, it's obvious now. But I'm just saying that the distance these guys are apart, these slits are apart, and how far the screen is. Notice as these keep getting bigger and bigger, think about it, the fringe spacing is going to rely a lot on how long lambda actually is, how far apart these are, because the further apart they are, the more ringlets there are. Then more opportunities to meet and cancel out. Okay? The further this is back, again, it changes the fringe spacing. Okay? So the fringe spacing is I'm just making sure, delta X is equal to, just get it right, N lambda L over D. Okay? So what that means is this. What's D? D is this. So again, in physics, it often just boils down to plug in the values to a formula and get the answer. Okay? So you're lucky in that way. That's good. There's D. This here is L, the distance between the source and the screen. Okay? Lambda is lambda, wavelength. Okay? And is there anything else? Oh, N. N is simply which fringe are you dealing with? Okay? In other words, is it the first one? Are you going from N0 to N1? Well, that's it. That'll be the distance between the central band. Oh, what am I doing?
You want to do N1 to
N0 to N1. But if you want to go N0 to N2, then you put 2 because it's twice that. It's the next one over. It is, yes, it basically, this comes down to a lot of, yeah, I know what you mean. You're putting that look on. It's like, are they actually all equally spaced? Well, they don't look very equally spaced, and when you really, really dig down into it, they don't actually look that way. But for the limit of the course, you just, it's fuzzy enough that you can call it that they're equally spaced. And they never really ask you for anything deeper than a couple of fringe spacings. Usually the questions in this part of the course are, what's the fringe spacing if you have to calculate that? And it'll just be delta X equals lambda L on D. In other words, just from the middle to the first. That's it. And the other question will be, what happens to the fringe spacing if I drag the screen out this way? Or if I drag the screen in this way? If I drag the slits closer together or further apart, what happens to the fringe spacing? So you can do that by just looking at the formula. And what's delta X? How far apart the bright bands are from each other. In other words, do you see the pattern open up, or do you see it contract? That's all they ask, really.
For a flat screen.
For a flat screen, nothing more complex than that. Okay. Over here, I found on this sheet here, diffraction simulations. So double slit, right? Look at this. I found this, and it's on the OneNote, which means you can have a look at it and muck around with it all you want. Okay. So I look at the wavelength, Now, they've clearly, what they've done here is they've said, okay, this is yellow light. So if I make the wavelength, get the wavelength shorter, it changes color. How cool is that, right? Because it's shorter wavelength, you're going back towards blues and greens and that. That's right, right? So it does that, and you keep on going. And so shorter and shorter wavelengths simply means that there are more and more wavelets coming out to interfere with each other. So you're just getting way more fringes. Okay, hard to see though on this screen. Let's try and make it a little bit nicer. But you can play with this all you like. So there's that measurement that you can manipulate. And the other measurement, if we just drag this back out, what are you doing? Drag that back out, spacing between the slits. What happens to the fringe spacing if the slits get closer together or further apart? Let's see, shall we? Why don't we find out? Okay, we're going to increase the separation. Why is that? Remember what I said before? If they're further apart, the two slits are further apart, more ringlets get out before they start interfering with each other. More ringlets, more interference. More bands if they're spread apart. If you squish them together, then they meet really early. And you get less and less opportunity for interference. Okay? And what's this one? Angle. Don't worry about angle. We don't really worry about that at this level. Okay? So there is double slit interference, and yes, probably in next lesson's lecture, you will see single slit. See, single slit implies being very, very simple, but far out, there's so much weird maths in it, which is all beyond the course, but it's still fun, and we could still have a look at it. So we're going to go to example 13. Below, here we go. A physics teacher has an apparatus to show Young's double slit experiment. The apparatus shown below, the pattern of bright and dark bands is observed on the screen, just like I showed you with my own little laser back then. Which one of the following actions will increase the distance delta x? Remind me, what's delta x again? So the distance between each of the fringes, okay, the bright fringes. That's how the pattern spreads out. That's delta x, okay? So which one of the following actions will increase delta x? Spread out, okay? Will decreasing the slit width? Well, the slit width isn't really a thing that we measure in double slit, okay? The slit width is set so that you get diffraction, okay? So in this respect, for double slit experiments, we don't worry about the slit width itself, okay? You worry about the distance between the slits. That's a measure that you actually use, all right? So decrease the slit separation. Yes or no?
If you decrease
the slit separation, will delta x get bigger? Yes. Yes, that's right. It will. Because there's less opportunity for the ringlets to actually interfere with each other. Okay? Decrease the slit screen distance. In other words, L. Bring the screen closer. Will that spread it out, or will it crush it in a bit? Yes, so no. I reckon it would make it smaller, not bigger, because if you drag the screen out, then those points where they interact are happening, because you know they're all divergent. That would spread them out, bringing the screen away, not bringing it closer.
That would make L bigger.
Yeah, that would make, yeah. So in other words, decreasing the slit screen distance, that doesn't make delta x bigger. It does the opposite. Okay?
With that equation, doesn't it make it bigger? Yeah. If L is bigger, the equation is bigger.
Here, delta x is equal to lambda L over D. So if L gets bigger, that gets bigger.
Yes.
Wait a minute. Yeah, that makes sense. That's right.
Oh, yeah, 'cause then there's
Yes.
Yeah.
So in other words, the question is saying decreasing that distance would make it wider, which is the opposite. It's saying, I'm just saying C's wrong. That's all.
Yeah. Okay.
So, which does make sense what you just said. All right? And then decrease the wavelength of the light. So again, less waves are getting through in the same time. Okay? So decrease the wavelength. Would decreasing the wavelength increase lambda? No, it's the other way, isn't it? All right? Okay. So that was a question, and now I had one more question for you. It was question 5, or example 5. Let's have a look at example 5. This is a very typical kind of question that they ask you, okay? The source, and this is a sound one. Okay, so this is a sound, well, it's very simple, okay? You don't have to do any maths in it or anything like that. The source is adjusted to produce sound of wavelength 2 centimeters. So crest to crest is 2 centimeters, all right? And the loudspeakers are placed 10 centimeters apart as shown. A microphone is placed at a point which is 100 centimeters from X and 101 centimeters from Y. The sound intensity there measured is, no sound will be detected. There will be a detectable sound intensity which is constant in time. There will be a detectable sound intensity which fluctuates slowly with time. And there is insufficient information to choose A, B, or C. Yeah. So I would be very hard pressed to say you would hear nothing because it would just really imply a perfect situation. But yeah, sorry. Yeah, from the speak. Well, oh yeah, from the speakers. Yeah. Well, how do you know that you're supposed to hear either a quiet spot or no sound? Well, the path difference is literally half of lambda, which are the conditions for destructive. So walking on a line this way, you'll get loud, quiet, loud, quiet, loud, quiet. It would be great to actually try that out one day.